I'm Samuel. I'm best known as the creator of Pydantic. So Pydantic started as a data validation library back in 2017, long before Gen AI, and it's still widely used outside of Gen AI. But as Gen AI became a thing, it was adopted fairly widely by both agent frameworks and by the provider SDKs to both for general API calls, but also to validate structured responses from models. Pydantic became a company back in 2023 when we backed by Sequoia. And then we released Logfire, our observability platform, last year. Pydantic is kind of relatively ubiquitous within Python. It's downloaded at the moment a bit over 350 million times a month. So it puts it somewhere like in the top 25 most downloaded packages. In terms of kind of public packages you go and use directly, I think there's requests, NumPy, maybe pandas that are really above Pydantic. So yeah, it's boring doing data validation, and it's kind of ubiquitous. I did have beloved on here as well, but I thought that was maybe a bit arrogant for me to say. But like, some people like it. So what am I talking about? When I wrote the CFP for this back in, I think, December, I was going to talk about this kind of opinionated blueprint for building Gen AI applications. I think an awful lot has changed since then. And obviously, there's also been a great deal of movement on what an agent is and isn't. There's been some relatively public disagreement in the ecosystem about what an agent is and how they should work. But also a lot hasn't changed. We're all still trying to deploy applications that are scalable and reliable and have at least a chance of actually doing what we thought they were going to do in production. And that is still hard. Despite how amazing models are, actually getting them to go and do the thing you want them to do is still not trivial. So that I'm going to use Pydantic AI and Pydantic Logfire, our observability platform, today to demonstrate how I think you should try and do that. But most of the points I'm going to make should be applicable outside of those two tools. I'm going to use, I hope the internet's going to work, because I'll actually run the examples against the model. So we may have some issues if the internet is being as poor as it was earlier. So I'm going to talk first of all about type safety when you're building agents. People think type safety is a like boring thing you need to get right when you're putting code into production. I think actually type safety is most powerful when you're trying to iterate quickly in development, when you want to be able to go and refactor your code and quickly correct all the places where it's now incorrect, right? As in, if you have type checking that's working properly, your IDE will show you exactly where your code is incorrect. You can go and fix those cases. You can generally like fix your refactor using Pyrite or your IDE without even getting around to having to run your code. Then you can go and run it to check it's actually right. And that's much, much faster than the untyped world where you need to go and run your code each time to work out where all the errors are. And that's why not just in Python that typing is popular, but like TypeScript in JavaScript is just ubiquitous because I think that's generally agreed upon. It's therefore very odd that the people who built the first wave of agent frameworks in Python chose to do things that meant they couldn't be type safe, but that's what they chose to do. And so that's one of the reasons we built Pydantic AI. MCP is talked about an awful lot, overhyped, but is actually, I'm a big fan of it, even if there is perhaps too much noise about it. And so I'll give some examples of where MCP allows you to basically connect tools to Pydantic AI and therefore get access to this like wide variety of different tools and more. And like I think that one of the frustrations of David Pereira, MCP creator, is that everyone thinks MCP is just for tools, and it can do a lot more. So I'll talk a bit about that. I'll try and explain how evals fit into the system. I don't know whether I'm going to have time to go fully through the example, but I'll do my best. And while I am going through those examples, I will show you where I think observability and tracing are useful, kind of essential when you're building these applications. So what is an agent? I don't want to do the like original what is an agent talk here really, but I think given that there still doesn't seem to be a universal agreement about how we define it, I think it's worth at least explaining what I call an agent so that we can agree on what I'm saying, even if you happen to have a different definition. So this picture here from Anthropic's relatively well-received blog post back, I think at the beginning of the year, talks about their definition of effectively what an agent really is. Now, this is very pretty and it looks nice. I don't actually think it explains particularly well what that looks like when you write code. So I think Barry Zhang, also from Anthropic's talk at AI engineer where he had this code is like, this for me is like the seminal definition of what we really think of an agent. Agents are models using tools in a loop. And it is kind of that simple. And I've got the link here, and all of the slides are up on GitHub, so you can get the link to the YouTube video. This is obviously pseudocode, so I'm not claiming this will work exactly, but the principle I think is very clear. There is, however, one distinct conceptual bug with Barry's code snippet here, which is that the loop never ends. And sure enough, working out when an agent should terminate is actually one of the harder problems that there is not a universally accepted answer to. Anyway, so enough pseudocode. Let's look at an actual example of some Pydantic AI code and see how it runs. So in this example, sure, we have some imports. We have a Pydantic model that defines a person, and then we define our agent. And we define our agent with an output type of person, and we obviously give it some instructions. And in particular, because we've set the output type, the agent is now generic in that output type. And so when we both at runtime result.output is going to be a person, but also in type checking terms, result.output will be a person. So if I run this example here, I'm very pleased with setting up a task that means I can run snippets from inside Markdown files in Z. So I had to do that. But actually what's probably more useful is to copy paste this example. And if I put it in here and save it as x.py, what you will see, yeah. So you can see, well, first of all, if you look here at the agent, you can see it's generic. It doesn't take any depth in this particular case, so depth is none, and it is generic in the person. So that results that when we get back the output object, that is a person. So again, if we go and access output.name, nice, that's fine. But if we tried to access, say, first name here, and Z was working properly, it would give us an error. You'll have to take my word for it that it will, because it's decided to like kill the LSP just before I started talking. Let me restart that and see if we get more lucky. And I'm now not in a project. Let me do, and now, yeah. You can see here that we're getting the type checking error. And this obviously seems trivial, but in a larger code base where we want to do a refactor and we want to decide our agent instead returns, let's say, a list of persons, a list of people, that is like incredibly valuable that suddenly we just get the type checking errors everywhere and we can go and refactor it. Again, I feel like this is an obvious thing that doesn't need to be hammered home, but yet we seem to be the only agent framework, at least that I have seen, that takes this really seriously. So someone somewhere must disagree with me, or at least not know how type checking works, like how to do generics, for example, to get this to work. So what you will notice about this agent is it doesn't actually do anything agentic at all, right? It's a single shot. It calls the LLM. The LLM processes the unstructured input and returns you some structured output. Pydantic, the framework takes care of doing the validation. We get back our instance of person. But even in situations where we don't have tool calls, we can already get into situations where we have effectively an agentic workflow. So this is more or less the same code, but we've added, or we've said this is now a historical person, and we've added a field validator, which insists that the person must be born in the 19th century. And we've been a bit unfair to the model, honestly, in that we haven't really told it that. We've said historical here. This doc string for the type would go into the description of the tool used for output, but I mean, it's not going to know. So if we go and run this example, it'll take longer, and it will succeed, and it will return a date that's correct. But what's actually going on inside here? If we take this example, again, copy paste it in here, and let's close that for now. And let's import add Logfire, and we can start to see what's actually going on in here. And we're going to add these 3 lines of code. So we're going to add Logfire into the example. Sorry. I spelled Logfire wrong, which is why it was complaining. And look, we're a company. We're building Logfire. We're selling Logfire. And so I'm obviously going to use that example, but like we are very, very dedicated to following open standards. So Logfire is processing data over OpenTelemetry. The instrumentation of Pydantic AI itself is just using OpenTelemetry directly. We have almost none of the you could send that data therefore to any OpenTelemetry endpoint. There'll be a few fields that are kind of Logfire specific, but it will just work regardless of whether you're using Logfire. And I think that's something we think is really important because we think if you look over the last 50 years of tech, open standards have won out. And so where companies have gone and decided to build their own tracing approach or not use type checking, not follow these open standards, I think they might succeed short term, but long term they're going to have an awful lot of trouble competing with the open standard that everyone else is backing. So if we go and run this example again, we'll see we use Gemini in this case. You'll see it made 2 calls to the chat and succeeded and in the end successfully output the right date. But if we open this example, so this is the Logfire dashboard. I will try to make it a bit bigger so you can have a better chance of seeing it. But if we look at the agent run we just had, there were 2 calls to Gemini, roughly similar kind of timing. And if we load the conversation itself, we can then go and see exactly what happened internally. So first of all, we had the user message, which was the original raw input. The model returned my date of birth is 1987, as you might expect. But we then performed validation with Pydantic. The Pydantic returned a validation error saying, no, the person needs to be born in the 19th century. And then the tool used that input from the messages to then try again and now change the date of birth and return successfully. And so even in this case where it looks like a kind of single shot extract some data, we already have this agentic workflow of looping through, effectively running our tools, validating them, and then trying again. So the other thing I should have said is I'm really happy to take questions at any time. So if anything I'm saying is unclear, please put your hand up and I'll happily try and take questions. I'm sure if you're unclear, someone else is unclear as well. Go on. Yeah, so I think it defaults to 1, but you can set retries here to retries to whatever number you like, and you can, if you're using tools, as I'll show you later, you can set it on an individual tool.
When the type was wrong, how did it construct the prompt on the second prompt to Gemini?
Yep.
I think I missed that part.
So you can actually see it here. So it's literally 1 validation error, and then we've taken the raw validation error from Pydantic. We're lucky enough that I think Pydantic's been, one of the advantages of having been around for so long is that I assume lots of Pydantic validation errors are in the training set, and models seem pretty good at understanding what Pydantic validation errors mean, even when the actual errors are not particularly descriptive of what you should do differently. I've seen it when we have some errors that are not particularly clear on things like time zones, where it will go and fix it, even though the error doesn't explain it, because presumably it's kind of seen it in the training set. So yeah, I don't know if we allowed you to customize it, but yeah, we basically dump the errors and say, fix the errors and try again.
Isn't this a bad example because the model kind of hallucinated a good answer to pass?
Sorry?
The model kind of hallucinated to get the validation to pass. For example, a human who would read that would say it's most likely 1987.
Yeah,
right?
but so in this case, we've added a field validator to get it to fail the first time, because in real life it will fail on very complex use cases. I didn't want to have a 200-line example, so I was basically unfair to the model. I almost just said fail the first time, just to show the principle of retries. In this case, you're right. What we would actually have done is we'd have put in the system prompt, the person is historic, and I could probably try it now. If I add this to the system prompt and I run the example again, it succeeds the first time round, right? It only took 1 message. It only took 1 call to the LLM. But this concept of, people call it reflection, being able to send the errors back to the model is incredibly valuable in more complex cases. Or where you just simply haven't got round to adding all of the stuff in all of your functional validators into your system prompt because you're in a hurry and you want to get it to work. Yeah, there's a question here.
In your original question, you said 1987
yeah.
specifically. What would happen then?
I have no idea. You're basically giving the model an impossible task because you've told it the actual year is fully 1987, and now you're saying that's not allowed. I don't know what it would do. I presume it would probably try and make it the 18th century, but 19th century, but who knows? Anyway, moving on to the next example. So although I would argue this is kind of agentic because it's got a loop, we haven't got tools. So let's look at an example where we've got tools. and we'll use this to show a few other, I think, really like powerful features of Pydantic AI. So this case, we have, again, we've set up Logfire. We've got some imports about database connections. We've got some code here to basically set up a Postgres connection. And at the moment, we can drop the table so that it's standalone examples. And we've added one table, which we've called memory, which has a few fields. So user ID, so it could use a different user ID for each, or it could be conversation ID if you wanted to like segregate memory by conversation and then value, and we've made it unique. And then we have this depths data class, which again, we've passed into, we set the depths type on the agent. So you'll see here, if we look at the agent definition, it's now generic in depths, dependencies, and the return type is string because we haven't set it, that's the default. And so this is the kind of simplest version of the like ChatGPT style like chat agent, but we've given it what people refer to as long-term memory, where we've added two tools here for record memory and retrieve memories. In this case, I made it really simple. I've set it up to try and filter on what memory to return. So yeah, what we're doing here in terms of using tools from Python function signatures is not entirely new. I think we've done some nice tricks internally with Pydantic to make it as concise as possible for the model, because we have, as you can imagine, great understanding of how Pydantic works. But the big difference is this CTX parameter here, which means not only can we get dependencies into the function without having to send them through the model context, but also that it's again type safe. So you'll see here that if I access context.depths.con, it is an instance of DB connection, and sure enough, it knows the signature of execute because of that, because I set the depths here to have an attribute, have a field con, and if I changed this signature here, say I thought by mistake that the run context was parameterized with int, not only do we obviously get errors inside the function body, but we also get this error here saying, wait, you can't use that function with that signature. So we're forced to use the same depths here, access it here, and then when we actually go and call the agent, we pass depths in here, and again, they have to be the right type. If I got confused and thought I was just going to pass in the user ID, again, type checking will come and tell me, no, needs to be an instance of depths. And so again, this kind of thing makes it really easy to go and refactor your code because you've got this type safety throughout your system. And as far as I know, no other agent frameworks don't offer this. So yeah, in our actual code, we're going to run our agent twice. Obviously, we're just doing it here within the same function. We're just creating a database connection. I'm telling it my name is Samuel, and then I'm running it again and asking it what my name is. Obviously, in this case, it's just within one function, but you can imagine that can happen over a long period. So if I go and run that example, you'll see bunch of calls going on. And yeah, sure enough, it was able, when I asked it second time, what's your name, to come up with my name. But the powerful thing here is like, sure, you can get a bit of an understanding from the kind of log style trace that we show here in the terminal, but obviously the real power comes from looking at the actual call inside the Logfire dashboard. So you can see here, we also instrumented async PG. I think this is one of the things that we at least think is incredibly powerful about Logfire, unlike other offerings in that space, is that it's a full stack observability platform built on OpenTelemetry, instrumenting both GenAI applications and GenAI code, but also the rest of your application. So we can here instrument async PG, and like not because async PG is some tool built into Pydantic AI, it's just a library we've gone and used, but it has OpenTelemetry instrumentation. So we'll see in here inside the first agent run, we are running one tool, record memory, and inside that span, we then have the query itself. And so we can go and look at exactly, we can see this query took 5.6 milliseconds, whereas the calls to OpenAI are taking like 1 second, like 1 second or so. 1 second, in each case, right? So we immediately get an idea of what's going on within our application and what's taking time, and is it worth optimizing that query by adding an index, or is it worth trying to work out how to like use a different model that's a bit faster? Yes, so the Logfire platform I'm showing here is a cloud platform that is commercial. We have a very generous free tier, so you can use it for free, but yeah, it's not open source and it's not available to run locally unless you're an enterprise. But again, the data we're emitting is OpenTelemetry. So if you don't want to use our platform, you can go and send that data to a JSON file or to one of the open source OpenTelemetry backends. I mean, honestly, Langfuse, who are one of our competitors, have open source, and they have instructions on how to run Langfuse with Pydantic AI. So if you really want to use open source tools, you can do that. We will succeed because Logfire is better, or fail if it's not. We won't succeed because we're trying to lock you in, unlike some other libraries, right? We think that like building on open standards not only is like valuable long term, but it forces us to go and build a great product rather than trying to find a way to lock people in. And I also didn't show here, like, we have pricing information, so you can see both aggregated, both on an individual call to the LLM and aggregated. So you can see here, this was the outer call, and you can see the like price was whatever that is, 0.1 cent, to make those calls. While I'm on the subject of memory, let me talk about another example of what. So that first example, as I say, AI. Go on. There's a question in the back.
OpenTelemetry and the standards. Oh, yeah, that will help. Thank you. So I see there are some Logfire statements for instrumenting async PG, for instance.
Yep.
If I understood, this would support any OpenTelemetry instrumentation. So if I wanted to instrument requests library, it should just work, right?
You may have to install an extra dependency to get the like requesting, but yeah, if you look here, we have like instrument an enormous bunch of different things, right? But more importantly than that, if you look at what's going on inside instrument async PG, this is just a convenience method. If we go to the actual definition, all we're actually doing is using, well, I may have to follow me for a minute, but like in the end, we're just using OpenTelemetry's async PG instrumentation. And so similarly, if there's another instrumentation, for example, there's some nascent instrumentation for the new OpenAI, what's it called, requests endpoint, you can go and use that, and the data will automatically just flow into Logfire, even if we don't have the method. So yeah, I was talking about like this example here of what people would kind of refer to as short-term memory, where instead of registering these tools for save and retrieve memories, we are giving the model access to the history of messages whenever you're making a call. So all of the conversation is basically in the context. So again, we're using Postgres, similar setup, except we're defining one table called messages. And again, this stuff is relatively similar in terms of depth, although actually I probably don't need that in this case. That's me forgetting to delete that bit out. But you'll see here, when we're actually running the agent, so we have this method to run an agent, which takes a prompt and the user ID. And the actual run of the agent is here, but what we're doing on the outside is I've used Logfire's like direct instrumentation method here to put a span around retrieving the messages, another one around recording the messages, but basically what we're doing is retrieving messages from the database before we make the call, validating them or coercing them with Pydantic type adapter to get a list of messages. Sorry, question.
So when you specify the output through a Pydantic model, are you changing the user prompt and appending some instructions in the user prompt so that model returns using that schema, or?
No, so what we're doing at the moment is we're using tools. So you can see here, in fact, it's made a tool call to a tool called final result, which is how we do structured outputs at the moment. We are in the process of adding support for Gemini, and OpenAI have specific support for structured outputs that don't use tools, and the other models do reasonably well if you basically give them the JSON schema as part of the instructions and say, return data in this format. Some of the simpler models perform better with that than with tool calling. Some prefer tool calling. We're basically going to offer both options. But like at the moment, we're using tool calls, but we're about to add support for basically the choice.
Okay.
So yeah, loading messages and saving messages afterwards. And again, if I go and run this example, we should have here. So you see the data coming in, and you can see those individual calls. And sure enough, again, it was able to work out my name because the second call had access to the messages from the first call. Yep. Sorry.
Memory, do you somehow need to add it to the prompt or?
So I've added message history here as a keyword parameter to the run, which is, yeah, and that is expecting, again, as you can imagine, it's all typed. So the type of message history needs to be a list of model messages, which in turn is a union of different message types. And we have this type adapter here, which will validate a list of messages. The only slightly niche thing here that we're doing that you would be a bit surprised by messages here is not a single message for each row in the database. It is a list from each call, and so we're actually validating a list and appending that to a list of messages. But like, yeah, effectively, we're retrieving the messages from the database and then just adding them into the context by whatever method the model would normally support.
Another related question is that many of these agents, like they make tool calls, they also respond with text messages, and then some of those could take a long time, or maybe multiple iterations. Do you support some form like a streaming, like a token streaming?
Yep. So you can stream. So I will see if I can update this example now to stream instead of returning a text. So we have a run stream method here, which is going to complain about a bunch of different stuff. So we want to do async for message in, no, it's async with as. See if that's got it right. Is that? Let me remind myself exactly the signature of run stream. See if I can like get myself. The autocomplete is not helping me, but basically we can iterate over it. Let me try one more time and see if I can go to the right definition and remind myself of the right way of doing it. So we return a stream run result. Stream run result has on it methods for, hopefully, if I can look down here, .stream. That's what I was looking for. And I want to stream text. And I think by default, if I look at the signature there, we have delta false, so it's going to return the message extending over time. But if I change that to delta equals true, and then I want to do end equals empty string, flush equals true, and I'll give it a more interesting question this time because it's not very interesting, it's just returning my name. I'll just comment out the first example. If we run that one now, you see it's like returning a stream which has been debounced to, I think, 0.1 seconds by default, because we can also do stream structured data as an output, but like, and I've then obviously, I forgot to update the rest of the example. But hopefully that answers your question. So that was the two memory examples, memory with messages. I said I was going to give an example of MCP. So this first example, we have a MCP server that we've built, which allows you to run Python code within the MCP server. So it's sandboxed properly with Dino, unlike some other offerings of like code agents, which are not properly sandboxed. This is literally giving you the like V8 isolate level of isolation between where you're running the code. And so in this very simple example, we're just asking the model to calculate the number of days between two dates. So if you ask the model just to do this normally, I think maybe it would be right, but A, you would have no way of knowing whether it was using the right logic, and models are not particularly good at simple arithmetic, so I think you would be unlikely to get the right result. But if you run this example, and the gods of Wi-Fi are with us, yeah, it's successfully gone and calculated the number of, has it not used the tool? That's great of it. Oh, did I not instrument that case with? I haven't added Logfire in, so I can just. So again, to see what it actually did, I'm gonna no. I'll do Pydantic AI, and we also now have an instrumentation for MCP. So, why is it? No, I don't want to add a random tab in there. If I run that example now, we should see that, and in this kind of time, it's correctly called the tool and returned the number of days. But if we come over and look at that code in Logfire, we get a we should get a pretty good idea of what happened within the run. So you can see here that we had the user prompt, and then it decided to call the run Python code tool, which is coming from MCP, and the code it asked it to run looks about right to me. But again, one of the powerful things by using this method for calling Python code means you can actually go and audit what Python code it ran and work out if it got it wrong, why it got it wrong. And in fact, I think someone leaked the ChatGPT system prompt last week, and that had a whole section on always call Python code if you're doing any calculation. Here's how to call Python code. Lots of pressure on the model to call Python code if it ever had to do any calculation, because that's how they do it as well. And I think they use similar stuff, like if you want to have plot a graph or anything like that, or display an SVG, I think those are all done through function calls or through writing code. And so you can see then our MCP server returned success and the output data. If there had been standard out, if there had been any prints in the Python code, it would have returned them as well. But this is where I think it's worth noting some of the things that make MCP different from simply tool calling, because MCP has this live connection with the host, with the client. If you have print output within, say this Python code takes minutes to run, you don't want to sit here just waiting, wondering what's going on. We can use MCP logging, where it will return the standard out chunks as they're being emitted from the Python code directly to the client, which you can then print within your application or send to Logfire and display within Logfire to work out, or any OpenTelemetry offering to display it there. Yeah, and you see what it's done internally is this one function call, as I say, and then summarized it again. Thank you. So I have spent far too much time talking about these things, and I will skip I've got another example of MCP using MCP Playwright's MCP server to browse the internet, which is much less reliable. Someone yesterday I was speaking to was saying they didn't like talks where everything went right. But so I had this example that I was pretty sure was going to fail to show that's not the case. But I'm going to skip past that because we've only got 10 minutes and talk a bit about evals. So if I look in here at our evals code, I'm going to talk you through this particular example. So I don't have very long, so I'm going to go fairly quickly. But again, me and the rest of the Pydantic team are down at the booth. So if anything I say now is not clear, please come and talk to us afterwards. But the very simple, the principle that we're trying to set up here is we have this agent to give you a time interval based on a user input. So in particular, this actually comes from a real life use case we have here, where we allow you to, if you're trying to search for a time period within Logfire, you can enter plain text here. So we want to write evals for this very simple piece of functionality to go from user description of a time range to the actual time range. And so that's the code we have here. The output type is this union of either basically success or failure, and an explanation of why, and a bit of detail on that. We have a function, a tool call for giving the model access to the current time. You could probably put that in the instructions if you wanted. And then, so this, in the end, there's an awful lot of hype and talk about evals, but fundamentally evals are just some method of doing something between a benchmark and a unit test on a function which is stochastic. Most often an LLM call, but in theory it could be any function that is has a probabilistic output. And so this is the fundamental function that we're trying to eval. It takes, as I say, an input, which is a type dict, which just does prompt and what the current time is. and outputs this union of basically success or failure. So the first thing we want to do is generate ourselves a data set. Now, we could get this data set from writing them out ourselves, or we could get this data set from looking at real-world data using Logfire or whatever you're using for logging or tracing to look at what users actually put in. Or Pydantic evals are like evals functionality within Pydantic AI has functionality for generating evals. So in this case, we're going to use O1. We're going to use a more intelligent model to get a good set of evals. We got a long prompt describing what it should go and do, that it should use these different judges, and there's a like relatively complex Pydantic model behind the scenes, which is defining the structure of the data that O1 should generate. So if we run this code, I won't run it. It takes about 70 seconds. It's one call to, in this case, OpenAI, and it will return us some relatively complex object, and we're going to write that out to a YAML file. So I won't make you wait for it. This is the YAML file that it outputs, which is basically a set of cases, names, the inputs for those cases, the expected output, and then the evaluators. So effectively methods. I mean, they're technically a class, but methods, which we're going to call to judge the success of the model. And we do quite a neat thing here where we also write out the JSON schema for the YAML file next to it. And this magic comment here means that most IDEs will give you basically type checking within YAML files. So it's the same thing if you're editing, say, GitHub Actions and you use a wrong key, it will normally warn you. So if I, for example, get a key wrong here, I'll get an error saying that like missing property now on this particular field. So we get sort of type checking even within the IDE when editing these files manually. Mostly we won't have to in this case, but obviously we can. Then the second thing we're going to do is, and I'll skip through some of this just to keep going, but we're going to add some custom validators to evaluators, excuse me, to that YAML file. You could do this manually by inserting these. We in this case we're using a script to basically edit the YAML file and add some extra evaluators just to save time. I can run this file and it runs basically instantly and outputs this second file. And what you'll see is, if I look at, for example, worth looking at the definition of these validators. So these are effectively, they're a data class for a number of reasons, but they're basically one function where we define some scores on how well the model has performed. So we have window is not too long, window is not in the future. We have user message is concise. Looking at the length of the message, we have agent called the tool. So here we are, this is a whole can of worms to go into, but we're effectively using the OpenTelemetry traces to look and check which tools were called within an evaluator. And then so these we're registering here, and so you'll see that most of the examples in YAML now have these evaluators added to them. The first run added the LLM as a judge in cases, so with a rubric which describes how the LLM as a judge should evaluate the return values, the output of running the evals. And so then from there, we get to this code, which is what we're actually going to go and run. So again, we're setting up Logfire. We're going to instrument Pydantic AI. Again, you don't have to. If you want to output this stuff locally and not use Logfire, you completely can. But we're going to run the evaluator, and then we're going to basically, in a unit test style, basically check that the pass rate, how many of those cases were successful, exceeds 90% in this case. And if we run this, it might take a bit of time. Oh, the internet's being good. We're running through those cases. They're all running in parallel, and it has come back and failed, and it has said, no, we got 69% of the tests were successful, not 90%. So just above that, we have the output data here in a table, which you could go and look through, and there's a raw JSON file that you can go and review to work out exactly what went wrong if you don't want to use Logfire. But by far the most valuable, simplest way of looking at this is to come over into Logfire and look at this evals run here. So this is that run I talked about. You can see, if I make the screen a bit bigger, the specific case is being run, but probably more interesting is to see this table where we're basically what I'm actually going to do is go back to 100% here and then zoom in like this to make it a bit easier for you to read. But you can then look at, for each individual case, which of the assertions passed and failed. You can see the metrics, like in this case, token usage and number of requests. And you can see that in this case, very often, this LLM as a judge test is failing, where it's saying, ensure that the message is in the second person, as in it's saying you should do X, rather than where it has said, maybe there's a more clearer example, it referred to I instead of you. So we can see immediately that one of the mistakes is that our system prompt doesn't tell it to talk in the second person and talk about you rather than I or they. And there are a few other ones that have failed with the actual, the time range evaluator has failed. I won't go and fix those ones now, but I will try to, actually, I'll show you one more thing, and then I'll go back and run that. So in this case, we're doing something similar, but instead we're comparing two different models. So we're using some other functionality in Pydantic AI I haven't talked about, is we have a lot of support for both writing unit tests and for altering how your model performs without having to go and edit your direct code. So in this case, we're using this context manager to override what model is being used within our application code, so we can run the evals with 4.0 and Claude 3.7 in this case and see how the two perform. And if I'll clear the screen here to make it a bit easier to look at. And if I run this case, again, everything's run in parallel, so although there's actually quite a few cases to run, this is reasonably quick. Quick to run. Again, there is the output here, but it's obviously a lot easier to see exactly what's going on when you look at the full output and it's finished. And if we come over and look at this run, we should see, if we look at this run first of all, you'll see that this is 4.0, got 70% success rate, and you can see that Anthropic is slightly better at 75%. And again, we can dive into individual cases and why they failed. But what's neat is because this is built into Logfire, this is observability data. If I take a case that failed and I want to look in more detail, I can then go into the individual spans related to this particular call, including my application code, and look at exactly what happened and start to investigate where the error might have happened or what the cause might be and look into fixing. Time is up, so I will finish off by saying thank you very much. The last thing I wanted to point out is Pydantic AI is not finished. We know we have a whole bunch of stuff more to do. We'd love to hear your feedback on where it's working well, where it's working badly, and we can react to that. But lastly, just kind of contrary point, we also know stability matters, and so we're going to push very hard to get to a version 1 this summer, and then be very careful about semantic versioning and not, at least intentionally, breaking your code anymore. Thank you very much.